In the last lecture, we introduced the smallest unit of a quantum state, and we said that this is called a qubit, which is essentially corresponds to our classical C bits of 0 and 1. The difference between the quantum bit and the classical bit was, while a classical bit can only stay in either the value 0, take either the value 0 or the value 1. A quantum bit, which is a qubit, can be simultaneously in a linear combination of the state 0 and 1. We also saw that while that is true, now if you are making a measurement, let us suppose that you make the measurement in a computational basis, then you would get either the state 0 or the state 1 with the probability which is given by mod A square by mod A square plus B square or mod B square by mod A square plus B square respectively. I also gave you some physical realizations of qubits, saying that they could be representing the spin half particle, its spin projection along some arbitrarily chosen direction like z direction, or it could be the polarization direction associated with a photon, or even the ground state and the excited states of an atomic system. Now we talked about the Pauli matrices, and what we are going to do is this, that the well-known Pauli matrices are sigma x, sigma y and sigma z, which are 0, 1, 1, 0, sigma y equal to 0 minus I, I 0, and sigma z is equal to 1, 0, 0, minus 1. Each one of this has an eigenvalue plus 1 or minus 1. For example, sigma z has an eigenvalue plus 1 corresponding to the state 1, 0 and an eigenvalue minus 1 corresponding to state 0, 1. You can yourself find out what are the eigenstates of sigma x and sigma y. Let me find out an arbitrary direction, the Pauli matrix in an arbitrary direction. Let's just call it sigma n. As you are aware that an arbitrary direction in space, the unit vector, has components which are x component is equal to r sin theta cos phi, y component is equal to r sin theta sin phi, and z component is r cos theta. If I take r is equal to 1, that makes the sigma n, that is the Pauli matrix along the arbitrary direction n, as sigma z times cos theta, which makes these diagonal elements cos theta minus cos theta, plus sigma x times sin theta cos phi, which makes it sin theta cos phi. Let me just write down here and then I will write it more compactly here. So I have got sin theta cos phi plus sigma y times sin theta sin phi, but you notice there is a minus I in this. So therefore it will be minus I times sin theta sin phi. You can use cos phi minus I sin phi equal to e to the power minus I phi, and then write this as e to the power minus I phi times sin theta. So this term is e to the power minus I phi times sin theta, and correspondingly this one is e to the power plus I phi times sin theta. Now it's very trivial to find out what are the eigenvalues and the eigenvectors of this matrix. Eigenvalue, as you know, you have to simply find out the secular matrix which is lambda minus cos theta, here lambda plus cos theta there, and of course these two elements just become negative, and then you find out the determinant, put it to equal to 0. If you do that, you get the value of lambda, that is the eigenvalue, to be equal to plus or minus 1. Now, which is not surprising actually. The eigenvalues lambda the reason why it is not surprising is because we had said that the eigenvalue along the z direction, which is an arbitrary direction, there is no God given direction called z direction, is plus 1 or minus 1. So, if I take an nth direction, that also should be plus 1 or minus 1. Now, you can use the same metric sigma n to find out what are the eigenstates associated with either of these eigenvalues. But I am going to be interested only in the eigenstates corresponding to lambda equal to plus 1, because that is what is the standard convention for the pictorial representation that we talked about. And if you just do a little bit of an algebra, I would urge you to do that for getting some practice into eigenvalues and eigenvectors, you will find that this eigenvector is given by cosine theta by 2 and e to the power I phi sine theta by 2. If you look at the slide here now, see what I have done now is this. I now take this state which I wrote down, that is the column vector cos theta by 2 and e to the power I phi sine theta by 2. So, this is my state which I will write as state theta phi. Pictorial representation that I am talking about is known as a block sphere representation. Returning back to the slide, let us look at the directions. I said that now this is a sphere of, does not quite look it on the slide, it looks a little ovalized, but on the other hand imagine it is a sphere of unit radius. So, it is a unit sphere, and what I am going to do is to associate every point on the unit sphere with a unique state, having a value theta phi. Now, let us look at what it means. Now, supposing I take a position, well, remember r is equal to 1. So, I take, let us say, theta equal to 0, phi equal to 0. Now, what is theta equal to 0, phi equal to 0? Okay, let me rewrite this state theta phi in a slightly different way. So, this is cos theta by 2 times 1 0 plus e to the power I phi sine theta by 2 0 1, or in our vector notation, ket notation, this is cos theta by 2 0 state plus e to the power I phi sine theta by 2 the state 1. Now, supposing I take the state which is theta equal to 0, phi equal to 0, put it here. You notice because theta equal to 0, this term becomes equal to 0. And since cos 0 is equal to 1, so theta equal to 0, phi equal to 0, which is nothing but the north pole in the slide that I showed you. So, north pole corresponds to the state 0. Look at that picture there. So, this is the picture on the slide. This is the point which stands for the point 0, that is the north pole. Now let us go to the south pole. Now if you go to the south pole, so I have got, remember that south, so north pole corresponds to the state 0. Now let us look at south pole. The south pole has theta equal to pi and phi is still equal to 0. Now that obviously stands for the state 1. Remember that I had written this format. So if I have theta equal to pi, cos pi by 2 is equal to 0. So this term goes away. Phi is equal to 0, so e to the power 0 is equal to 1. And this is sin pi by 2, which is equal to 1. So the state is 1. So if you go back to the slide, you find that this is your state 1. Okay. Let us go to a slightly different point. Let us consider the point where the positive x-axis meets the equator. The point where the positive x-axis meets the equator now, since it is on the equator, theta is equal to pi by 2 and phi is equal to 0. Now you can immediately go back there. Theta equal to pi by 2 means cos pi by 4, which is 1 over square root of 2. E to the power 0 is equal to 1. Sin pi by 4, which is again 1 over square root of 2. So this state is 1 over square root of 2, 0 plus 1. Remember that I had called this the diagonal state, one of the basis of the diagonal state. And likewise, you can convince yourself that the point where the negative x-axis meets the equator, that is simply the other basis in the diagonal states, that is 0 minus 1. Like this, every point on the Bloch sphere stands for a unique quantum state, and the theta phi value can be obtained. I will later on talk to you these states which lie on a Bloch sphere, they all are what are known as a pure state. What is pure about it? We will be talking about as we go along. The next question is that how much of information is there in a qubit? Now remember, in principle, a qubit contains infinite amount of information. Now what is the reason? The reason is that, remember, my theta and phi are the parameters in that, and theta and phi's expansion in terms of binary digits may be essentially non-terminating. But we have told you that in spite of the fact there is huge amount of information contained in that qubit, much of this information is not really available to you, because when you measure it, you either get a state 0 or you get a state 1. You can calculate what is the value of sigma z in this context. You can easily see it by finding out the way the expectation value of a quantity is calculated. We have seen that the state is given by cos theta by 2 e to the power I phi sin theta by 2. So my sigma z operator is 1 0 0 minus 1. So the expectation value of sigma z is given by the row vector cos theta by 2 e to the power I phi sin theta by 2 multiplied with this, trivial matrix calculation which will give you cos theta as the expectation value of sigma z. And likewise we can determine sigma x. Now remember that I have mentioned to you earlier, though I have not yet proved it, a quantum state cannot be exactly copied. There is a theorem which we will be proving as we go along, that there is a no cloning theorem of quantum state. But then you imagine somehow we have prepared identical copies of quantum states and we are able to make a large number of measurements. So I can calculate the expectation value of sigma x. By that I can find out what are the directions nz and nx. And we remember that I have nx square plus ny square plus nz square is equal to 1. So by these calculations I can find the values of nz and nx, but the signature or the sign of ny will remain undetermined. So this is what we talk about. Now the point then is this, that we have so far said that when you make a measurement, you get either a state 0 or a state 1 with a probability. Now this probability will allow you to determine, so for example if I have a state alpha 0 plus beta 1. Now if I make a repeated measurement on identically prepared copies, I will get state 0 with a probability alpha square by alpha square plus beta square, and the state 1 with the probability beta square by alpha square plus beta square. Now these are the probabilities which we will get, which will enable us to determine the magnitudes of alpha and beta. Is there a way of finding out the relative phase? Supposing I consider a state for convenience psi, which is equal to 0 plus 1, but I have a e to the power I theta there, and I normalize this with a factor 1 over square root of 2. Now I know if even in this state, if I measure the states in a computational basis, I would get the state 0 or state 1 each with a probability of 1 by 2. This is what comes from here. But how about the information on theta? Can I get it? Now if you are making a measurement in the computational basis, you cannot. But I will just now show you that if you make a measurement in a diagonal basis, okay, you will be in a position to find out the information about phase. So let us suppose I have this state psi, which I have said is 1 over square root of 2, 0 plus e to the power I theta, theta is the relative phase, by square root of 2, 1. And let us measure it not in a computational basis, but in a diagonal basis. Now in order to make the measurement in a diagonal basis, I must first express the states 0 and 1 in the diagonal basis. Now recall that my diagonal basis is plus is equal to 1 over square root of 2, 0 plus 1, and minus is equal to 1 over square root of 2, 0 minus 1. If you do a little bit of algebra, this will tell you that 0 can be written as plus plus minus by square root of 2, and 1 can be written as plus minus minus by square root of 2. So this psi that I wrote down just now can be now expressed as this 0, there is another 1 square root of 2 here, so I get a 1 over 2 plus minus plus e to the power I theta by 2 plus minus. Now, if you rearrange these terms, you find that this is given by, here I will write it as half of plus half of. So, let us look at this. Let me write it down and then it becomes clear. This is fairly straightforward algebra, but let me write it down. See, basically what I have done is this. I have taken out an overall e to the power I theta by 2 out, so that this term now has a factor e to the power minus I theta by 2, and this term has e to the power plus I theta by 2. Now, if I now collect the plus, then I get e to the power minus I theta by 2 plus e to the power I plus I theta by 2 divided by 2, which is cos theta by 2. And likewise, the coefficient of minus becomes minus sin theta by 2. Remember that this is an overall phase factor. And in a quantum state, as we have stated earlier, an overall phase factor does not matter, because a state psi and another state which is c times psi, they have no physical difference. So therefore, this is not going to matter to us. But suppose I am now making a measurement in the plus minus basis. The probability with which in the diagonal basis I will get the value to be plus is cosine square theta by 2, and the probability with which I will get the minus will be sine square theta by 2. So therefore, this measurement in the diagonal basis gives us some information about the phase. So far we have been talking about a single qubit, but notice that we all realize that a single qubit is just one bit of information. It may be with linear combination, it may be lot more informative or may contain lot more information than a classical bit, but nevertheless we are still talking about one qubit. Now, in order to do computation, we need to go to more and more qubits. As you are aware, in classical bits, we talk about situations like where, let us say 0, 0. Now suppose I talk about 2-bit situation. What do I have there? I have 0, 0, 0, 1, 1, 0 and 1, 1. And likewise, if you take 3 qubits, 3 classical bits, then you have 8 different combinations. Now, in that case, how do we handle this situation? Now, what we are looking for is the qubits which come from a composite system. Looking at this slide, suppose I have a composite system. Let me call it A and B. And let us suppose alpha is a basis in the subsystem A and beta represents a basis in the subsystem B. Now, I define my composite system like this, that is alpha beta AB, and if I take vectors in the subsystem A and subsystem B as alpha prime beta prime, then the corresponding bra multiplied with this ket gives me. Now, analogously, I can now define an operator in this composite space. Suppose I talk about this operator, this is a direct product sign, MA cross NB. Now, it acts on a state psi phi. So, what happens actually is, the state MA acts on the state psi, NB acts on the state phi, and I know that an operator acting on the state gives me a linear combination of vectors in that subspace, and likewise here. So I would get a situation like this. That is getting more and more complicated. So as I said that the classical bits, referring to classical bits are 0, 0, 0, 1, 1, 0 and 1, 1. The quantum 2 qubit state will then be a linear superposition of states alpha 0, 0, 0, 0, etc. The same normalization holds good, alpha 0, 0 absolute square up to alpha 1, 1 absolute square is equal to 1. Now, we will talk about 2 qubit system and its extension to n qubit system in the next lecture.